Regarding control, I learned something more. That is the actually Petrotel distinguished lecture in chemical engineering Arabic control. It is delivered by a distinguished chemical engineering scientist working in India. I also welcome Professor Anurag Pandey of ICT Mumbai and a very distinguished scientist who has very kindly accepted our invitation. I now invite Professor Gundru to say a few words about the Petrotel lecture series in chemical engineering.
Thank you, James. Good evening, everybody. The Petrotel Distinguished Lecture Series in Chemical Engineering at IIT Kanpur has been made possible by endowment from Dr. Anil K. Chopra, who was the winner of 1976 in chemical engineering, when he was at the University of Houston in 1982 for the second chapter. And he is the president and chairman of Petrotel Incorporated at Texas, USA. Actually, we say Petrotel, actually supposed to be Petrotel. Anil received IIT Kanpur's Distinguished Alumnus Award in 2010 for outstanding entrepreneurial contribution to the field of petroleum, software and energy. Anil's entrepreneurial skills eventually gave him to start Petrotel Incorporated in 1999. His company's vision is to help find major sources of hydrocarbons in India and across the globe using the latest technology available in a few multinationals. One of the first conducting projects of Anil and Petrotel in India was the seismic and certification of Reliance's onshore and offshore blocks, leading to the biggest discovery of gas in India. Petrotel helped Reliance put together the very first field development plan of the Dubai field. Today, this field produces over 1 billion standard cubic feet per day of gas. Rumor has it that Dubai offered Anil solution to Reliance, which Anil politely turned down. Anil's work led to another giant discovery in the Teji Basin in India, the GSPC. Today, Anil Petrotel is recognized worldwide as an industry leader in oil and gas field consulting in the areas of enhanced oil recovery, reservoir characterization and simulation, coal bed methane production and exploration technology. We have had 9 distinguished speakers in this series, namely Professor M. Sharma was the first one in 2004, then Professor Gandhi, then Professor Joshi, Professor Shimra, Professor Anand, Dr. B.D. Kulkarni, Dr. Ramaswamy, Dr. Vijayarathan, Dr. Devan Thakkar. On our 2014 speech, Petrotel speaker, Dr. Pandit, adds further distinction to the series. I now invite the head of department, Dr. Shankar, to introduce the distinguished speaker.
Thank you, Professor Gundru, and good afternoon all. Welcome, Professor Pandit, to our department. It gives me great pleasure to introduce Professor Anirudh Pandit as today's distinguished speaker, who is currently a research scientist and a professor at the Institute of Chemical Technology at Mumbai. Professor Pandit earned his BTech in 1980 from BHU, Banaras University, and his PhD from the University of Mumbai in 1984. He was an associate lecturer while he was a PhD student at the University Department of Chemical Technology, and he was working under the guidance of Professor J.V. Joshi. Between 1984 and 90, he was in the Department of Chemical Engineering at the University of Cambridge, where he was associated with Professor J. Davidson. After returning to India in 1990, he joined UICT Mumbai as he is a professor now. While at Cambridge, Professor Pandit worked on bubble breakup and design of multi-phase reactors and developed many novel designs of gas-liquid contactors and new impeller designs. While at UICT, he initiated a major activity in the area of hydrodynamic cavitation. He has been singularly responsible to propose, promote and apply the phenomenon of hydrodynamic cavitation for intensification of physical and chemical processing applications. He successfully exploited the cavitation phenomenon for a wide variety of operations such as crystallization, emulsification, nanoparticle synthesis and processes such as esterification, oxidation, etc. His work on microbial cell destruction for water disinfection has been recognized by International Maritime Organization as the most proven technique for ballast water treatment among 7 other developed by scientists in Japan, Germany, US, etc. His unique creative approach of using fundamental knowledge coupled with simple, elegant experiments, has resulted into novel gravitational reactors. He has authored over 300 publications, 3 books, and over 10 chapters. He has 5 patents to his credit and has guided over 32 PhD students. Professor Pandit has been actively involved in many committees related to harnessing solar energy, extending chemical engineering principles for drying of forest products, and water disinfection for potable water. He is currently involved in setting up of Cavitational Application Center at USC to exploit phenomena of cavitation of physical and biological transformations. He also served on the editorial board of several international journals. Professor Pandit has received numerous awards in recognition for his research contributions. I'll name a few here. He has been awarded the IICT Credila Award, the Distinguished Alumnus Award by UAA, and the Best Teacher Award by USCT on 7 occasions in the past 15 years. He was elected as Fellow of Indian National Science Academy of Sciences, Bangalore, National Academy of Sciences, Allahabad, and INSA in Indian National Academy of Engineering and Maharashtra Academy of Sciences. I would also like to add that Professor Pandit traces his academic lineage to Professor Sharma via Professor Joshi, and all 3 of them have given the Petrotel Distinguished Lecture in the last 10 years. That's indeed remarkable. And I now invite Professor Pandit to deliver the distinguished.
Thank you, Professor Shankar, for your kind introduction, and good afternoon to all. We have a bit of a problem, as usual, in terms of presentation, but I'll try to see whether the videos which we are supposed to have been integrated into the talk, I may have to sort of keep switching to show you the videos. The title which I have chosen today to talk about essentially is a very mundane title: the heating and cooking devices, energy and cost analysis. The reason for choosing such a mundane title and talking about things such as cooking is just wanted to show you that how much of science there is really which can be exploited, which can be learned, which allows you not only to publish papers in the top journals, but also come out with a product which is likely to have a huge social impact. So it is not necessary for a scientist or a researcher to sit in his own ivory tower and do research and not being bothered about whether that research is being put to use or not. As IIT graduates, I am from IIT PHU, which is now IIT PHU. We all paid minuscule fees. I paid fees approximately 480 rupees per year and 120 rupees of hostel fees for a period of 1 year, and 500 rupees or maybe 550 rupees were paid per year as a tuition fees. And the quality of education which we got is phenomenal, and we owe it to our society that who has subsidized our education and how we can return that particular favor, and that favor can be easily returned without compromising science. And that's why I've chosen this particular topic, which is sort of an ongoing effort since 1995-96, and if I have time, I'll tell you the stories associated with that. And that is why I have chosen this topic as heating and cooking devices, because look at any cooking operation, it essentially involves chemical, physical, biological transformations, as the transformations we learn in the area of chemical engineering. Each of these transformations are associated with energetics. Each of these transformations are associated with kinetics. Each of these transformations are associated with equilibrium processes. And if one looks at these basic processes from whatever chemical engineering which we have learned, it is also possible for us to model this particular system, try to understand the intricacies and the limitations as well as the controlling steps in completing this particular transformation. And once you do that, then as chemical engineers, we try to remove these limitations to speed up these particular processes. I'll give you some examples in due course when we talk. What was the motivation of doing something like this? The motivation is India being a largely agriculture-based economy, we have a huge quantum of biomass, and I'll give you some statistics to start with, just to justify, as all engineers do, that you have chosen a particular topic for research, and the people are likely to ask a question, why you have chosen that particular topic. Either that topic interests you, or finding some solutions based on those topics are likely to have such huge impacts that it is likely to make you famous. Whenever you try to do something, you try to do something to get recognition. Now the recognition could be in terms of money which you earn, or recognition which you get in terms of your publicity. Now both essentially are extremely satisfying results, and we carry out this particular research not only to satisfy our inner curiosity, but also while doing that to see whether we make a reasonable amount of money, and while doing that come out with a product which is likely to be useful to the society. And as an agricultural economy, is it possible for us to look at this particular agricultural produce, which is essentially biomass, food grain, leave apart for the time being, we'll come back to that later, and whether this biomass can be put to use, and a lot of work has been going on, including your mechanical engineering department, where biomass conversion to bioethanol is being practiced. The simple reason is it's easier to burn these liquid fuel or gaseous fuel as compared to burning of solid fuels. But still, 70 or 80% of the India's population rely on burning of solid fuels, so it is necessary for us to have a look at it. I will see that in due course of time. If I just do some basic calculations, back of the envelope calculations, on an average, 10 tons of biomass is produced per hectare. You don't have to do anything. The typical annual rain cycle and the seeds which are there will produce that much quantity anyway. If you want to cultivate it, you can cultivate it and bring this particular number right up to approximately 30 tons. Now 1 ton of biomass, in principle, all the carbon and hydrogen associated with it is converted by delignification, all the saccharification, converting cellulose to glucose and to finally to ethanol, is capable of producing about 20 liters of alcohol per ton. You can take it and stretch it up to about 30 liters as well, but let us consider for the average 200 liters of alcohol per ton of biomass. If I say that I want to satisfy the entire energy requirement of the country, then you will require about 150 million hectares of the land area to satisfy the need of our country. If I want to burn the biomass as such, because while converting biomass to ethanol, we lose out on certain calorific value, you would require about 80 million hectares of land. If you want to meet the current energy consumption of China, then you will require about 450 million hectares. If you want to match the current energy consumption of US, you would require about 4,100 million hectares, whereas India has only about 300 million hectares. So obviously, we cannot be aspiring to meet this particular requirement of energy consumption and get to the level of US or China, because we just don't have the capacity in terms of the requirement of land mass. Now when you want to burn the biomass as such, which 70% of the India's population still rely on, the rural population rely on, what you realize that these biomass stoves or biomass burning processes are run extremely inefficiently, and they are environmentally polluting. Not necessarily in terms of carbon dioxide emissions, because this carbon dioxide is a neutral carbon dioxide. The same carbon dioxide will be taken up by the plant, and the plants will grow again, and they will keep on recycling it. But in terms of emission of particulate matter, which is responsible for respiratory diseases, lung problems, eye infections, tuberculosis, so on and so forth. And as engineers, if you keep looking at these particular processes, you will realize there exists a huge scope, because the systems are run inefficiently. If the system was running efficiently, then obviously it has reached its thermodynamic state and the equilibrium state or maximum efficiency state. But because they are run inefficiently, any process for that matter should be looked upon as an opportunity if it is run inefficiently. That is what the basic motivation for this work is. In terms of, again, liquid fuel consumption, in Indians use about 2 barrels of oil equivalent per person per year. With an approximate population of 1 billion people, we are going to use approximately 2 billion barrels per year, which is approximately 300 million tons per year, about 100 million tons, and India currently processes about 150 million tons of crude in terms of refining capacity. 180 million tons from other sources such as coal, hydro, etc. But where does this energy go? In terms of per capita consumption, equivalent to 500 kgs per year, global is 1800 and US about 8000 kgs per year. So energy consumption of India is bound to increase as well as China, and we must be gearing for it. Now, if you see this energy pie, what you see here, industry uses about 27% energy, transportation about 12%, agriculture about 2.7%, commercial AC at 0.8%. This is I am talking about absolute energy, not necessarily in terms of electricity. Okay? Residential uses about 55.6% of energy. And where does this energy be utilized for residents? Lighting is a fraction of it. India has a huge population. We have to prepare food for these 1 billion people. 2 square meals a day are required. And you know how elaborate these Indian cooking practices are. They are all essentially multi-step synthesis processes, and you all know the number of steps in the process as they increase, that is a conversion. Even if you consider that, let's say, I am preparing one particular item which requires 7 steps, and I am converting each step with 90% efficiency, 0.9 multiplied by 7, ultimately the efficiencies are going to be substantially lower. So if there exists an opportunity, can we have this 7-step processes converted into 1-step processes? Of course there are, and that is where you see these ready-made food packets. People are exploiting this. You have everything out there, put it in the oven or a microwave, and you have a ready meal available. The energy consumption is going to be substantially lower for you. But while preparing that, have they looked at that particular preparation of ready-made food, looking at the fundamental and basic principles which are involved in cooking? It is not. 40% of the total energy consumption of the country goes in cooking alone. Now people talk about energy efficiencies in industry, energy efficiencies in car, energy efficiencies in lighting. That is addressing the other 60%. And nobody is looking at this 40% chunk of energy consumption, which is run so inefficiently, with average efficiencies ranging anywhere between 15 to 20% in terms of thermal efficiency. That means only 15 to 20% of the net energy which is there in the fuel is actually being put into cooking food. So there exists a huge opportunity for us to look at it and see how this particular number can be improved. What sort of an economic impact we are likely to have as a result of this? So we did some back of the envelope calculations. Biomass consumption in terms of the rural population is equivalent to about 124 million tons of oil equivalent, expected to grow at a rate of 5%. In the year 2000, we would have consumed about 165 million tons of oil equivalent. Even if half of the cooking practices are replaced by efficient cooking methods, assuming we save about 40% of efficiency, we are talking about 25,000 crores of rupees. Now, if I relate it to something else, I will tell you the number. It is mind-boggling. Indian rural women folk spend on an average to collect a firewood or to collect a biomass which is required for cooking. On an average, they spend about 7 days a month. Right, 7 days a month. If I have a cooker which is, let's say, 2 times, 3 times more efficient, thermally more efficient, then 7 days will reduce to probably 2 days, 2.5 days. So there's 5 days of equivalent earning power of the women folk, assuming that if they go on a daily wages and earn about 250 rupees per day, and if you cumulatively calculate this particular number, the productivity available and the saving which is available is to the tune of 4 lakh crores of rupees. Now these numbers are not negligible numbers. If one can look at it, you can imagine the kind of impact it is likely to have. And that is why I have said that the payback period for any of these activities is usually less than a year, and of course we are contributing to the reduction in the CO2 emissions. So cooking fuels in India, as we use it, that 70% of the rural areas essentially rely, 85% of those rely on biomass, 15% are only the commercial fuels, such as, let's say, kerosene or LPG or coal or whatever. 56% of the urban population uses LPG. LPG consumption has also increased. With the government removing subsidies, it's likely to have a huge impact. So the outline of today's talk is going to be basic introduction, which I have already given. So I'll run through a couple of slides very quickly just to recap what we have talked about. What is the motivation and objective? We need to look at the fundamentals of it and see how the solid biomass essentially combusts, essentially burns, what sort of emissions are coming out of this, how we can model the system and have some sort of a quick calculating method based on the graphical user interface approach, the integrated equations which we'll see in due course of time, and then we need to validate this with the help of experimental analysis, and we'll try to draw some conclusions. Now this is the total energy consumption which we saw. About 40% is consumed in cooking, 14% is commercial fuels such as gas, kerosene, coal and electricity, 86% is non-commercial and includes wood, biomass, cow dung, so on and so forth, as you see in this particular picture. Now this is how they are conventionally burned. You have a 3-stone fire, which was the original device, and even when you go camping, this is exactly what you do. Get 3 stones, start burning the biomass, put your vessel on top and try to cook a meal. Then people thought about improving thermal efficiency, so they came out with mud pots, which is Abhinav, Olav, Pavan, which has got a chimney associated with it, which creates some sort of a suction required to supply the combustion air. Bhagyalakshmi, Astra, all of these, there are approximately 43 different cooking devices, and not cooking devices, stoves, which have been reported by MNRE, Ministry for Non and Renewable Energy Resources, and none of them have been scientifically analyzed from first principles. You can imagine the state of science related to one of the most important devices which is used in the cooking practices. Improvements are there by using a metal stove, Janta, Navajyoti, rocket stove, Harsha stove, Purja, all these definitely improve upon efficiency, but still, what are the level of efficiencies I am talking about? 3-stone fire, about 8 to 12% thermal efficiency. Single and 2-pot mud stove, 10 to 20%. Improved upon in open fire pit and raised grade, 15 to 20%. Improved metal stoves, about 20 to 25%. The bullets in the blue out there essentially tells you the basic conclusions of each of the transfers, each of the slides which we are talking about. So what it clearly indicates that the available stoves are having a very low thermal efficiency and they consume a large quantity of solid fuel. So we need to address this particular issue. In addition to the consumption and loss of fuel in terms of its calorific value, there are huge health effects which are associated with it, such as respiratory diseases, lung problem, tuberculosis, eye infection. You can see a typical picture which is very familiar for the people who have had experience in the rural cooking methods. Whenever a system is efficient, obviously the emissions will be less. So whenever we are trying to design an efficient system, we are naturally addressing the issue of the emissions. The more you make the system efficient, less is going to emit to the environment. So in terms of exergetic loss or in terms of thermodynamic efficiencies, you are going to be nearer to the limit. So whenever the biomass is burned, it essentially passes through these 4 stages, and we'll see how these stages are. It gets dried first, or needs to be dried first. Then the volatiles from the biomass get devolatilized, and these volatiles burn as a homogeneous combustion, and when all the volatiles are emitted and burned, whatever is left with the carbon, which is char, this char burns in the form of a heterogeneous combustion. So these are the 4 stages which are occurring, and these stages sometimes, depending upon the design, they operate either parallelly or sequentially depending upon the design. And since we need to know what sort of energy is required for cooking practices, which will come a bit later, we need to be able to channel these particular sequential processes so that we extract maximum out of it. So motivation is rural population is not having access to LPG, they are still going to rely on the biomass. So availability of large biomass making the wood stoves as a ready-made option for rural India. But increase of these stoves will be similar to talking about 18th century, 19th century England, where they used to have coal as a fuel to warm, and then it used to produce so much of smoke that they had to ban it in terms of heating. As a result of which they discovered gas or oil, and that burning became much more efficient, which clearly indicated that from those point onwards, or from those time onwards, solid burning has always been a problem. Solid burning stoves has always been a problem and have caused to the emissions or increase in the emissions to the surroundings. To design, so the objective is to design a solid fuel burning stove meeting the requirements of low emissions and high efficiency. The said objective is achieved. Now I am looking at the science part of it. We need to identify the reasons where all these 4 or 5 reactions which we talked about, or the transformations which we talked about are occurring. Whether it is possible for us to design it in such a way that whatever particulate emissions are coming out, these particulate emissions are trapped, and then they are going to burn. Obviously only the inorganics will come out, which can have a micronutritional value, can be used as a fertilizer, or can be used as supplement in terms of micronutrient requirements for agriculture. So we need to understand the basic combustion kinetics of solid fuel. So we need to know what is the typical composition. We need to understand what is basic theory of combustion. We look at a single particle and packed bed of wood because we just don't use one particle. We need to have an ensemble of particles to supply the required quantity of heat to cook a particular meal. And then we need to look at what are the ignition methods, whether we need to light it from the bottom or whether we need to light it from the top. All these need to be looked at because each of these will contribute to either increase or improvement in the efficiency or decrease in the efficiency. So we do start with our proximate and ultimate analysis of wood, which also tells me about what is the calorific value associated with this wood. Now wood is going to be available in different forms, geometric forms, and what particular device which I use will be in a position to accommodate different types of shapes of the wood particles. So these are the basic reactions which are occurring, which I said: evaporation, simple water associated with the biomass getting converted into vapor. Then pyrolysis of the wood, which results into availability of char, some volatiles, some additional tar, but they are essentially hydrocarbons. In the process, being an endothermic process, it also produces certain quantity of carbon monoxide, carbon dioxide, and they need to be burned. Of course, you can't get it out. Then you have a homogeneous combustion of all the volatiles which are coming out, and finally the heterogeneous combustion of the char of the carbon which is associated with it. So in a packed form or a packed bed form, you will find that the char is existing at the top. There is a flame front or an ignition front somewhere in between, and unreacted fuel exists at the bottom. So essentially when you light it from the top, the volatiles come out, system gets dry, volatiles come out, you burn those particular volatiles, and the ignition front propagates downwards till it reaches the bottom where all the volatiles are removed, and then the ignition front starts moving upwards in the form of heterogeneous combustion. And that is one of the figures. I don't think this particular thing is likely to work. If not, then I need to go back. Interestingly, we have been burning wood for so long, and this particular figure comes from Europe. Nobody in our country has done this. So this is a combustion of a single wood particle. Now you can see how the wood particle is combusted. But if I supplement it with an air, what happens to this as well? You see it has started glowing again, and ultimately that carbon which is remaining in the unburned form also gets completely burnt, and you are left with a very small fraction of residue, which is the inorganic material which is there. Let me just show you one by one and then we can go back to it. Okay? This is the packed bed, and what you see, this answers your question. You see there is a char, a reaction front, and unreacted fuel. So when you put it in the form of a bed, as exists in the form of, and you light it from the top, what you see here, how the ignition front is moving now, with the charge getting generated at the top, and when the ignition front reaches the bottom, all the volatiles have come out, and then the ignition front will start moving from bottom to top again. Only when you light it at the top. However, if you light it at the bottom, the air which is coming out from the bottom as a primary combustion air, that primary combustion air does not see a flame. The flame is somewhere downstairs. That heat which is generated by the flame is given to the wood particle on top. The wood particle on top devolatilizes, but those volatiles do not see the flame, so the volatiles don't burn, and it produces a lot of smoke. Whereas if I do this from the top, burn it from the top, I will find out that when I burn it from the top, I see whatever was the movie which I had shown earlier, that you don't see any smoke and the ignition front moves from top to bottom and then again bottom to top. Right? These were the videos which I wanted to show you, which essentially tells me how this entire operation of the combustion can be looked upon, and how this combustion operation essentially can be modeled, provided the computer agrees with it. Yeah, good. Okay. So bottom lid, you see a lot of smoke on the side because the bottom part is having a flame which is supplying the heat. But how does a flame or an ignition which is somewhere propagates downward? The air is coming from bottom to top, and the only way the portion of the fuel which is below the portion of the ignition front can increase to a temperature of ignition is through by radiation. So we have to consider the heat which is getting transferred by radiation and then address the issue accordingly. And this has all been considered in the case of the model. Anyway, I have given you a picture. This is what it is. So we start modeling this particular system. So what do we model? We model the steady state calculations. We estimate the effective flame temperature and excess air. We write the expressions and develop a model to understand how the suction of air which is required for combustion is actually entering the system, and then the propagation of the ignition front. After the ignition front has moved to the bottom and only char is there, we need to model the heterogeneous combustion, and then all of this can be put in the form of a graphical user interface. So you start with a steady state energy balance, which is simply heat liberated by complete combustion of wood is equal to heat associated with the flue gases, heat which is required to heat the incoming air to the flame temperature, heat which is required to heat the fuel to the ignition temperature, so on and so forth. So all these energy balance needs to be done. And if I look at the quantum of air which is used out here, you see as the quantum of air increases, obviously the energy which is utilized to heat up that air will be used up and the flame temperature will go down. Now what sort of flame temperatures are required for cooking purposes? Now, if you are going to do baking, then you bake it at about 250 degrees centigrade. If you fry it at about 220 degrees centigrade. If you want to steam it, you will steam it at about 100 degrees centigrade. So the flame temperatures which you are getting are actually several times higher than what you require to cook the temperature. And as you all understand, that using energy in terms of its quality for the specific application in mind is likely to be the most effective and efficient way of using energy. How many of you know what is the exergetic efficiency of the geyser, the electric geyser which you use? In terms of first law of thermodynamics, you say that this is the electrical energy which I have supplied, and the water has been increased in its temperature mCp delta T, and you find that the electrical consumption is matching that, so I am having 90% efficiency or 95% efficiency in terms of transfer of enthalpy equivalent from electricity to heating up of water. But if you consider the exergetic efficiency of a geyser, electric geyser, this exergetic efficiency is of the order of 3%. That means 97% of the exergy, that means the electricity has a capability to do 97% more work, but we are actually using this particular highest form of energy, electricity, in just using a mundane device such as heating of water, which we could do quite easily using a biomass. This type of an approach is necessary, and we will need to understand how the cooking practices are actually contributing to the lower efficiencies which have been reported. Similarly, we can draw and develop a simple model which is very similar to design of a chimney. You have a hot column on one hand and a cold column of air on the other hand. There is a pressure gradient which is created. This pressure gradient will allow the air to pass through the packed bed of fuel particle. It has to overcome the pressure drop. You can use Erwin's equation. I am not talking about rocket science here. This is all basic principles of chemical engineering which you have learned in your undergraduates, and these are the concepts and these are the equations which you are going to put to use in developing a particular product. If you do that and you understand the height of the bed versus the kind of suction which is required, because the suction should create sufficient quantity of air to carry out the combustion completely, and you find taller the bed, then larger is going to be the suction which is going to be created. But is it practical? If the bed is so tall, let us say the bed is of the height of about 10 feet, then of course it will create a great suction, but it will be like preparing herbal khichdi. I have a flame front which is 12 feet away from the vessel where I am trying to cook the material, so the losses are going to be substantially higher. So I need to have a proper balance between the two, and this balance can be achieved by understanding the basic transfer of heat when the fuel is getting combusted and releasing its heat associated with it. So this is the basic system which we are trying to model. You have fuel bed, we have a grate on which the fuel is resting, you light it from the top, that's the ignition, you have a char, the ignition front, unreacted fuel, and then the air is introduced from the bottom, and the heterogeneous combustion is that D part where all the volatiles have come out. So I can write again a simple balance, take a strip within this, and I can write in terms of complete energy balance. And the only assumption which I make, since the air is moving from bottom to top, convective heating of the fuel which is below the ignition point or ignition layer is not likely to get heated because of convection. But it is still propagating from the downward direction. The only reason why it is propagating in the downward direction is because of the radiation is hitting that particular layer of the fuel. So radiation is the main mechanism causing the ignition front to propagate. Radiation decays exponentially, that is why the lower part of the bed will be still cold, and as the flame front keeps on propagating downwards, it receives more and more heat as it approaches the unburned fuel part. So local absorption of energy in the bed is directly proportional to the heat flux. Heat flux is the calorific value multiplied by the cross-sectional area multiplied by the calorific the ignition front, and this will allow you to estimate what is going to be the energy delivery rate. So ignition front velocity can be estimated by writing a similar balance, and this can be used to determine the burn rate and a power delivery. If I know the ignition front velocity, which is dependent on many factors such as shape of the wood particles or shape of the biomass particle, the moisture content associated with it, all this can be modeled quite easily and will allow you to calculate the flame propagation velocity. Flame propagation velocity multiplied by the cross-sectional area will give me the heat flux, and depending upon how fast I want to cook the material, I must have a cross-section of bed which is capable of burning at a specific rate in terms of so many kgs or so many grams per minute, delivering the required quantum of power. Again, an experimental match with the model indicates that approach appears to be right. So when I simulate the ignition velocity in the fuel bed, depending upon the quantity of air which I am heating, which is essentially supplying the combustion oxygen which is required, I can estimate the flame propagation velocities. If change the quantity of air, if I have a different quantity of moisture associated with it, as you can see from here, more the moisture, more is going to be the energy which is going to be utilized for drying off that particular moisture. As a result of which the flame propagation velocity will go down. So when I start with the fuel with a known quantity of moisture, I will be in a position to estimate what is going to be the rate at which the flame is going to propagate in the downward direction. All of this is present in the form of a simple stove. Now stove is what? You have a chamber in which the fuel is packed. You have a secondary air which is supplied from the bottom. Why it is supplied from the bottom? It is supplied from, secondary air is supplied from the annulus, not the bottom. Primary air is supplied from the bottom. This heats up the secondary air, and when secondary air comes out, provides hot air for the volatiles to combust at the top, and you increase the thermal efficiency of the system. So secondary air is required to burn the volatiles at the top, whereas primary air is required to sustain the combustion ignition front as well as liberate energy for the ignition front to propagate. So you have primary air, so you just model the system as if it's a packed bed system, and you write down all the balances. So make certain assumption in our model. System is one-dimensional, gas is described as an ideal gas. Fuel particles are of the same size. You can accommodate any fuel particles, spherical, cubes, stakes, or whatever it is. The model can take care of that. Bed wideage is constant and remains so. This may not be true, as you can see, as you saw from the first movie, where initially when the air was not there, then it was capable of maintaining the original shape of the wood particle. But the moment air was there, the wood particle sort of disintegrated. So which will result into decrease in the voidage, which will increase the pressure drop, and progressively the rate at which the air is going to be available is going to go down. Since the bed size is small, gaseous combustion reactions are controlled by kinetics without any limitation in terms of mixing of these gases, which is oxygen as well as flow gases, and particles are thermally thin. That means it doesn't have a significant thermal inertia. When it catches the fire from the surface, it is capable of propagating till the core of the particle. So the four successive sub-processes are modeled: evaporation of moisture, pyrolysis, homogeneous combustion, and heterogeneous combustion. So we start with essentially the gas phase analysis, gas phase continuity equation, gas phase energy equation, and similarly for each of the gases which are going to be present, and similarly we do for solid unburned wood, moisture, and char, and we need to write similar equations for unburned wood, for moisture, char, in terms of continuity equation and also in terms of energy equations for the solid material. We know the initial conditions because we are lighting it from the top, and the propagation of the ignition front is going to be from top to bottom and then reversing it. So I have initial conditions, and then I start the boundary condition in terms of the densities, in terms of the starting temperatures, the location from where I need to simulate my packed bed combustion. These are the typical thermochemical properties which I use, and these are the properties for which the simulation has been carried out. I mean, this can be done for any of these. So I have a bed height of approximately 10 centimeters, width of 20 centimeters, particle size approximately 5 millimeters, particle density is wood density, bulk density, then bed voidage is whatever value which you get, inlet air flow rate, whatever that, the space step in terms of simulation, so on and so forth, and I see what sort of the results I get. And you can see here the match between the predicted value in terms of temperatures which are reached versus time. And this I see the fuel mass loss is stream and the rate at which the fuel mass is combusting. Now if I know the rate at which the fuel mass is getting lost or getting combusted, I can calculate the energy delivery rate. Whether that energy is being utilized by the cooked material or the material which is getting cooked is the second issue which we will address in due course. All of this can be put in the form of a graphical user interface, and I can essentially design my solid biomass stove based on the parameters such as particle density, particle diameter, bed height, fuel amount, distance from the stove and the pot, the length and breadth and the width of the chamber, which gives the adiabatic flame temperature, the suction which is created, and the rate at which the ignition front is going to propagate. It gives you again the calculation in terms of graphical user interface based calculation which tells you the basic parameters. So once I have this graphical user interface, very similar to you have a ready-made software, you keep on plugging and find out what sort of efficiencies, what sort of not efficiencies, but what sort of combustion rates which we are likely to get from different designs of it, and then you need to fabricate those particulars and test it, and we'll see what happens in a minute. So you see here is the flame propagation velocities or ignition velocities of the order of about 1 to 4 millimeters per second. So that is the rate at which the flame is propagating. So if I know the height of it, I know how long my fuel is going to last, and whether that time is sufficient for me to cook the material or not, I can calculate it independently with the knowledge of the energy which is required for cooking practices. So now we will run very quickly through the the experimental analysis, where we have varied the parameters such as particle size, air flow rate, bed voidage, bed height, stove geometry, multi-pack bed, and I'll explain it to you in a minute. This is one of the stoves which has been developed and marketed, which has an efficiency in excess of 50% because it's a post-draft stove, and of course, as we see that it is capable of sucking air, but it is capable of sucking air only when the required temperatures are. So initially you still require a forced draft. After the flame gets established, then you are in a position to switch off the fan and the stove will run effectively. So what was done, this entire assembly which contains the stove, the pot, was mounted on a weighing platform, and this entire weighing platform was covered with a drum. So the only air is available through this port, and the exit was at the chimney, and this allowed me to measure the loss of weight of the fuel as a function of time based on the indicators of the weighing platform. It could also, I could measure hot wire or a hot anemometer, which allows me to measure the velocity here, velocity at the exit, and I can collect the sample and analyze it in terms of its gas content to satisfy or to validate my experimental model. This is typically wood particles, the type of experimental device which we use. Ignition at the top of the fuel bed. This is how it starts burning. This entire thing is put in the form of a drum, and this is mounted on a weighing balance as indicated earlier. And I get information related to how the change in the fuel size, fuel particle size, and what sort of temperatures with the help of thermocouples I am able to get. So I am using mango wood particles with a moisture content of 12%, and the dimensions are, it's cube 15 millimeters by 15 millimeters. The only reason why I have used that since we have a model which takes into account the specific shape, I just wanted to validate the model. But the model can take care of any shape if you want. But what it clearly indicates that initially it's very slow, then it peaks up, then it starts going down. Usually, this is not the observation which you do when you start cooking the food using gas. The moment you start the gas, it starts rising up, remains for a specified period, and then goes down. And the temperature of the gas flame, as we use in the LPG flame, is of the order of 1200 degrees centigrade. Whereas if you remember earlier, the maximum temperatures which we were able to get was about 850 to 900 degrees centigrade. So there is 300 degrees change in the temperature of the flame which is created by biomass as against the flame which is created by using LPG. Now whether it is making any significant difference, if not, and the gas burners are much more energy efficient as compared to wood stoves, and the only reason is it is capable of controlling the rate at which the energy is being delivered. Now this has some major implications in terms of thermal efficiencies. So this is how you see here that in about 12 minutes time it reached 100 degrees centigrade. The moment all the combustible matter has combusted, the temperature starts going down. Now this is that rate at which the energy which is getting delivered, but you should have the device which is capable of accepting this particular amount of energy. Now all these next 7-8 slides essentially tells you the various heat fluxes which we are able to get. Any boiler designer will design a boiler with a specific heat flux. And the but the optimum heat flux at which the boiler will give you maximum thermal efficiency, which is in the range of about 88 to 90%, is when the heat flux is of the order of 20 to 24,000 kilocalories per hour per meter square. If you do more than that, then it is incapable of accepting that much quantity of heat. Obviously, more heat is going to go out through the flue gases, which will result into loss in the thermal efficiency. Right? So the particles which could be tested in terms of fuel particle size, air supply, primary and secondary, bed cross section, bed wattage, bed geometry. Again, it gives you particle with high surface, too high a rate which reduces the efficiency. Too large particles, the combustion cannot be sustained because it has got a very high thermal inertia. So the particle, for it to catch fire and to raise its to ignition temperature, it takes a lot of heat. It cannot sustain itself, and you have to have a frequent lighting which is associated with it. All this essentially tells me the different shapes, different ways of introducing primary air, secondary air have been tested out there. And once the bed is ignited, natural draft stores are capable of sucking required amount of air comparable to forced draft. So initially, what it clearly gave out that we need to have a forced draft only in the initial stages till the bed catches the fire the way I am expecting to catch from the front. So the flame temperatures, then I can accommodate the entire quantity of wood in different forms, and I will explain it to you in a minute. Just keep on looking at the efficiencies which we are talking about. We are still hovering about efficiencies in the range of about 16 to 22, 23%. So the only way I can improve this particular efficiency is to deliver, to control the energy delivery rate and manage my heat flux to be in the range of about 20 to 24,000 kilocalories per hour per meter square. So this again tells you how the smoke level changes, and all this essentially are linked to the characteristics of the particles, the surface area to volume ratio, so on and so forth. So we came up with different designs. The wood could be adapted or could be added to these 6 chambers, or 6 chambers can provide the quantity of air which is required for cooking by filling the wood in between, and this the next figure gives the way different experiments were done. Wood packed in here, wood packed in between, wood at the top essentially to light that, and then observe how the rates are changing. Now this is very similar to a wick stove. The wick stove is known to have a much higher thermal efficiency as compared to a primer stove. Okay? And you see how effectively it is combusted, and you can validate that assumption of no significant change in the bed voidage if you see that as it has burned, but it has remained more or less the same. Now you see here that you are able to get in excess of 30% efficiency for item C, that is if I pack this particular fuel inside 3 wire cylinders. If I use 2 smaller wire cylinders, then the flame cannot sustain itself because it doesn't generate sufficient energy for the flame front to propagate. So I need to have some critical thickness, and that thickness works out to be approximately 6 centimeters, 60 millimeters, and all this. So you look at this, initially high, then maintains it for some period, and that is what gives you maximum thermal efficiency. So I need to have a control over it, so I can have a burn rate over cross-sectional area. Now initially when you have material which is at room temperature and you want to heat it to 100 degrees centigrade, its heat pickup capability is initially very high. So you need to supply energy at a higher rate which it will be able to accept. However, as the temperature approaches 90 degrees centigrade, delta T is gone down, and if I keep on supplying heat, it is incapable of taking it out. So what type of a geometry I can think of? Can I think of a geometry which is conical in nature? Because in ignition front velocity is the same, and as the cross-sectional area changes, I keep on reducing the cross-sectional area, keep on delivering lower and lower energy. As the delta T goes on decreasing, then I will have significantly higher efficiencies. Indeed, such devices are capable of giving you efficiencies in excess of 60-65% in terms of thermal efficiencies of these wood stoves. Right? We have now designed a stove, assuming that we are on the right track. What do we do with these stoves? The stove has to have a cooker associated with it. The cooker is capable of taking up different quantities of material. So diameter of the combustion chamber, which is capable of accommodating different quantities of wood, because and you can match this or get this particular burn rate. So ultimately, I don't want to spend a whole day in cooking my meal. I have a certain restrictions in terms of the time available, and that time essentially is going to be 1 hour. So I need to finish my cooking practices or cooking method in 1 hour. So all these sub processes have been just a review of that. So we move to an eco cooker. So we came up with a device to go with our biomass stove, which can also be used with a simple gas burner, and this device essentially is indicated out here. I have pots and pans, and then a bottom cover. The pots and pans are put very similar to a pressure cooker, but doesn't develop any pressure. This is the final assembly. Now this final assembly can be put either on the biomass stove or my gas stove, depending upon whatever you have. Right, this is a larger scale version of it, which is capable of cooking about 120 liters of cooked food, capable of feeding about 300 students from a mess, and the cooked food is very good. And you all know that slow cooking is probably the best to bring out the flavors of it. At the same time, we also tested, not cooking efficiency was the only criteria. We also wanted to check whether the food which is cooked in this is maintaining its nutritional values, it's maintaining its texture, it's maintaining its taste. So fortunately, we also have a foods department in ICT. So we roped them in terms of a testing panel, and we asked them, look at the nutritional value of it, look at the vitamin content of it. Food cooked this way, food cooked in microwave, food cooked in pressure cooker, food cooked in open vessels. Now we had a comparison, and in fact, we came out with approximately 17 publications from this particular work based on the kinetics of loss of nutrients or enhancement in terms of taste of this. Right, so this essentially tells me the assembly. I have this bottle where I take water. This is the water which you can use for bathing purposes of the cooking part is over, because you can drain that particular water. The hot water is still available to you. About 10 or 15 liters of water is available, sufficient for one person to take bath. Then I put all these assembly in it. You see these holes out here? These holes provide the passage for the flue gases as they come out, and you extract the heat from these flue gases as well, increasing the thermal efficiency of this particular device. Then you put a primary cover, and then you put a secondary cover on top of that, and what you see at the bottom is essentially a burner which gets lit. We could get 65 to 74% thermal efficiency as against 20-25% we are talking about. That means we are saving nearly 70% of the fuel, 3 times less fuel consumption is there. Working principle, I match the optimum heat flux, which is about 20 to 22,000 kilocalories per hour per meter square. I reduce the heat loss by having double wall, and the thickness or the gap between double walls was actually arrived at by doing numerical simulations to find out what is the minimum thickness at which the circulatory currents will be completely stopped. So we arrived at that doing numerical calculations, doing CFD analysis of that early shut off. It is not necessary for me to keep on heating the material. The sensible heat which is retained in water is sufficient to cook most of the mass, because cooking as such, the reactions of cooking as such doesn't take any additional energy. Once you have temperature reaching 100 degrees centigrade or whatever temperature, rice starts cooking above 76 degrees centigrade, dal starts cooking above 92 degrees centigrade. Once you are able to get that particular temperature, maintain that particular temperature for a specified period, you get material perfectly cooked. I'll ask a question later on. And then because you are mounting one on top of another, you are using the classical principle of chemical engineering of multiple effect evaporation. The material which is getting heated from the bottom produces steam, heats up the material at the top. Those who have been to Puri will understand and see how the prasadam is served. There are about 21 vessels mounted one on top of another, and there is single fire at the bottom. Right? What happens is, the bottom vessel is taken out after it gets cooked, and a new vessel is put on the top. By the time this top vessel reaches, it takes about 12 hours or so. In 12 hours time, it is perfectly cooked. But you are using a steam economy, it is going to be of the order of 10. 1 kg of steam is capable of evaporating 10 kgs of water because of this multiple effect evaporation system. So this is a cooking device which was jointly developed, available in different sizes in terms of 3.5 liters to 160 liters. Thermal efficiency is in the range of 60 to 70%. This is already I have explained it to you. But what happens is, the material essentially is not agitated. If the material is not agitated, you don't know how it is going to cook. And the problem occurs when the material starts swelling. So you start stratification. Hot water remains at the top, and because of its low density, it cannot be circulated. So I need to design a system in such a way that it is capable of accommodating the circulation or convective currents associated with it. I have this, so I have 4 different design vessels where I provide the passage for convective currents from the bottom, from the side, and this results into a substantial saving in energy again. Approximately additional 10% improvement in the thermal efficiency can be obtained. So we did a numerical simulation of that. We took a quarter of this particular vessel, we addressed in terms of how the stratification is occurring out there, how the layers can be circulated to supply the necessary heat which is required for cooking purposes. This resulted into additional 15% increase in thermal efficiency. Right, so I'm talking about this, and I think only a couple of slides are there. We are talking about in terms of possible saving of the order of 12,000 crores. We also analyzed the kinetics of cooking. Very simple device. We developed a model which was very similar to essentially a shrinking core type of a model. That model was validated. We calculated the activation energies of that. All this is published. So we need to have a degree of cooking, and it can be assessed in terms of degree of gelatinization. This is rice which is cooked for 5 minutes, rice which is cooked for 10 minutes, rice which is cooked for 20 minutes, rice which is cooked for 40 minutes at a specific temperature. And what you see here, the transparent part is where the rice is, the starch is completely gelatinized, and the semi-translucent or opaque part is the core of the rice which is not getting cooked. So it validates my assumption of a shrinking core in terms of uncooked mass, and I can get all the information which is necessary in terms of the rate at which the cooking can be done. Now this I can fit it by using the simple first order kinetics or whatever kinetics I feel, and I can estimate the values of rate constant for these cooking processes. Now this is still a batch cooker, capable of feeding 150, 160 liters and capable of feeding about 300 to 500 people. But there are midday meal schemes of government of India which is feeding 20,000, 50,000. How do you handle that? Now that was done by developing a continuous cooker which is capable of feeding approximately, currently we have a model which is cooking 300 kgs per hour of cooked rice, 100 kgs of raw rice, which is capable of feeding approximately 300 people per hour. System is very simple again. This is a pilot which we developed. It's essentially a screw, and you will use different materials with the knowledge of time which is required for cooking. So once you know the cooking kinetics, designing such systems for chemical engineers is no difficulty. Right? If I have dal which takes longer time, I add dal out here, I add rice out here, I add vegetables out here, because each of which at a specific temperature require different lengths of time. I need to modify the subsequent flights in such a way that all that material is mixed up and I get a perfect khichdi. If I want to cook rice, I can have only rice. So the capacity of the cooker will depend upon what is the material which you are trying to cook in. Right? So we also studied the residence time distribution of solid and the liquid. So what we like is a uniformity of cooking, avoid the dead zones, and then heat transfer from jacket to the fluid. And we now need to have low shear, otherwise all the grains will get smashed up and I will get a paste of a cooked rice rather than a rice itself, and I need to look at the rice. So this is typically two setups which we tried, 5 kgs per hour and 100 kgs per hour, and we have now got a device which recycles this hot rice as it is coming out, heats up the water, takes out that particular heat, and then that particular hot water is fed back into the initial stages. Right? So I am recovering heat, and now I can work with overall thermal efficiencies with 88%. That means only 12% of the energy which is required otherwise. Can you imagine? Now we are talking about 40% of the energy consumption of the country being addressed, and you have the capability now to reduce that particular consumption substantially. This is a photograph of the final assembly of 100 kgs per hour. We ran this particular system at ISKCON, where they are feeding about 22,000 students at a time. They start at 2 o'clock in the morning. By 8 o'clock, all their rice requirement is cooked, ready, and since the rice is coming out continuously, you just need to transfer the casserole gets filled. As soon as the casserole is filled, you transfer it to a vehicle which takes it. So let's see if I can. This is just an indication in terms of what sort of impacts which I would like to have. I would like to acknowledge all my students out here, and I will leave you with the final. video which while that video is being run, you can ask any questions. And I thank you all and thank the Department of Chemical Engineering for inviting me to give this Petrotel lecture. And I hope I have done some justice to it. This is the continuous cooker, and you see how the rice is coming out, fairly free flowing, and you see the container which is getting filled as it is coming out from the other end. Thank you very much.
Thank you. We have time for one or two questions.
Either I have made it too simple or it is still not glamorous enough. Yeah.
So, can you please explain how you have this exergetic efficiency?
Yeah.
3% of electric
Okay.
electric heater.
Yeah, for electric heater. I knew that I would get a question to that. The objective is to heat water for bathing purposes from, let us say, 25 degrees centigrade to at the most 45 degrees centigrade. Now, effectively, to get water at 45 degrees centigrade, ideally I can use any heat source which is capable of heating it to 45 degrees centigrade with a temperature gradient maybe 10 degrees centigrade plus or 15 degrees centigrade plus. So effectively, I would be using an extremely low quality energy. It is sufficient for me to do that. On the other hand, instead of using such low quality energy, I am using energy which is capable of evaporating the water, capable of doing many more amount of work. So, the final temperature which I get and its distance away from the surrounding temperature, if I use energy which is substantially away from the environmental condition, then I am actually losing out the exergy associated with that energy. So exergy essentially defines the quality of energy which I should be using to get a work done. It is capable of doing significantly more quantum of work, but I am actually doing and extracting a very small fraction of the work, and that's why the exergy efficiency of electric geyser is only about 8%.
The only problem is if you kind of go for the very high exergetic efficiency, only problem would be that the
size of the equipment will go.
Rate will become very slow.
Well, yes and no. Ideally speaking, if you ask me, if I'm, let us consider only the fact that I'm using hot water for bathing purposes. The easiest way is use biomass. If I don't have biomass, use gas geyser. Right? Gas geyser will have significantly higher thermal efficiency, exerted efficiency as compared to electricity. So electricity as such has been converted to 40% efficiency from the actual energy content. And then I am using it, on one hand I am using biomass to produce steam and it's producing electricity, and other words I am using that particular electricity to heat water.
So you are getting very high efficiency. So is it because of the design of the heating vessel, or is it mostly because of the heater? But what I understood is that you are using the
it's the combination. It's a combination of both.
So in the rural area, if they use the rural the heater itself, the farmer itself, and you are heating vessel,
Yeah.
then will that work or you?
Of course it will work. In fact, that is what I am trying to say. Let us say I have developed let's say a biomass stove which is thermally more efficient, and I use a cooker with it. Right, the cooker which we have developed. Now you will work with approximately 60 or 70% efficiency as against 15% efficiency which you were working earlier. So the quantum of fuel which I require is going to be 3 times less. So instead of rural women folk spending a week in collecting month's wood, they need to spend only 2 days to collect that much quantity of wood. So 5 days equivalent in terms of their own working capability is available for them to earn. Now how you actually do that is a government policy which you have to decide. But but that is how these numbers of 4 lakh crores have been estimated.
You had a chimney.
Yeah.
Which, obviously took the hot air. What was the temperature? Can that heat be utilized in terms of reheating the inlet air?
Yeah, actually the design is done in such a way that the secondary air, which is being supplied at the top of the fuel bed, where the volatiles are getting burned, is getting preheated because it is going through the annulus. The role of chimney essentially is only to enhance the suction of air. If you see a particular vessel and you monitor the flue gas temperature as the flame is hitting the vessel at the center, and I keep on monitoring the temperature radially out, then you'll find by the time the flue gas escape the vessel and come out, its temperature has dropped to about 180 degrees centigrade from an initial temperature of 800 degrees centigrade. So you have already extracted. However, if I have a small vessel and a big flame, without having the capability of extracting heat from the flue gases, those flue gases are going to go out. In fact, the two-pot design, the mud pot design which you have, the fire is only in one pot. And the second part, where you cook, your fire is required where you are roasting materials such as chapatis or rotis. Whereas the flue gases as they are coming out are perfectly capable of cooking dal, rice and other things. And that is how you improve the thermal efficiency of the system.
Second question is that you didn't say much about the particulate.
Yeah. As I said to you, the particulate emissions will automatically reduce when your combustion efficiency improves. One. Second, if the air velocities which I am actually introducing as primary and secondary air are not sufficiently high, then it will retain the voidage of the bed and the particulate emissions will not get created at all. And the bed arrangement is such that you have only in the initial part, you have a flame which is at the top. Now the flame is somewhere in between. So even if the particles which are getting created out there are going to get trapped because of the unburned, not unburned, but the biomass, burnt biomass in the form of char which is at the top. When the volatiles burn in the form of flame, you don't produce any smoke, you don't produce any particulate matter. And that can be handled by appropriate distribution of the secondary air which is required. Typical biomass contains about 60 to 70% of volatiles. So you know the rate at which the volatiles are going to come out. To burn all those volatiles, what is going to be the secondary air which is required? So if you distribute the total energy supply in terms of primary and secondary in such a way that it ensures a complete combustion of the volatiles on the top of the bed and that will not produce any particulate matter.
I think we are in close because of time constraint. So let us thank may I ask Mr. Petrotel give this moment on behalf of the department? Looks very simple, but it's actually a very complicated process when sometimes is really dancing best. I should also thank the laptop because it worked. And all the volunteers and help from and finally to you too, Mr. John, and hopefully you enjoyed as much as I did this time. Thank you very much.